Last time we were talking about context-free grammars and how we can use the LL parsing process to convert them into an NPDA. I'm also getting the last homework assignment to you. It probably won't be due for a while, just because we have a little bit until the end of the quarter. And I don't want to make things due before they have to be due. That said, keep in mind your other classes and ensure that you're not giving yourself a massive crunch at the end of the quarter. There will be this last project, this last assignment in this class, as well as an exam. So there's still a bit to come. This is the summary slide. So we talked about this last time, just converting into an NPDA in a form that mimics the LL parsing process. And then we were going to get an example. So the example was with this grammar, and we wanted to create the NPDA that models this process. So remember, there are three states, Q0, Q1, and Q2. Q0, the transition from Q0 to Q1, the purpose of that is to put the start non-terminal on the stack. Q1 is going to be where all of the transitions occur, both those that read the input character and map those to a character, a terminal that's on top of the stack, and also a replacement where we take a non-terminal that's on top of the stack and replace it with a set of symbols, that sequence of symbols that represent how we could expand that non-terminal. Do we feel like we can get started with this, or do we want to see an example gone over beforehand?
I would like to see, yeah.
See the example? All right.
Especially if we got the time.
Yeah. So all we need to do is make sure we have that transition from Q0 to Q1 pushing S onto the stack. There it is. Then we need the transition rules for every production. So we're going to look through the grammar and we're going to be able to pop an S, push an A, an S, and a B. Pop an S, push a capital A, pop an A, push, and I'm reading this backwards, but it's an A, a capital A, and a B. You push them in that order so that what's on top of the stack when you're done is the first symbol. And pop an A, push a C. All of those stay in Q1. Then we need the shift rules to shift past input symbols. So that's going to say, read an A from the string and map that to an A that's on top of the stack. Same with a B, same with a C. And then we have the final state transition, going from Q1 to Q2 on an empty stack. Questions on this process? How we derived each of these transitions, what they mean? Ends up looking like this. So if you don't have some kind of image of this NPDA, go ahead and draw it, because we're going to use it to do an example parse on the next slide. So we have something like this somewhere in our notes and or memorized in our head. I can give you the string for those of you who are still copying it down. It is ABCAB. So you're only looking ahead at the next character. But the question now is there any ambiguity or guessing that you have to do when you parse this string. The way that I think that you should do this is to utilize an image representation that is kind of a side-by-side view of the stack, the state, and the look ahead. So we're going to start by saying what's on the stack. We're in state Q0, and the current character that we're looking ahead at in the string is the first character, the A. So the next thing you would do is transition to Q1, which pushes that. We transition, we're now in Q1, and we still have not read past that A. So continue this process by now using the transitions in the NPDA on the last slide, and continue to draw a history of these stacks, a time by time slice, until we have read past the last character of the string and have an empty stack. Does that make sense? People have enough information to get started? Make sure we're on the right track. What's the next step?
Since we're looking ahead for the character A, we can get it in the next transition.
Yeah.
So we pop the S and we replace it with the transition A, S, and B. Then we can pop the A.
Yeah.
Then we can read the next character in the string, which is B.
So we can move past this A. So this B here represents the next character in the string. Since we move past the A by popping them both from the stack and reading it, using that concept of a shift transition. Yeah, go ahead and finish this off.
Well, do something. ASB, wouldn't it be A as a bottom?
We read from right to left. We push from right to left so that what's on top of the stack when we're done is the left-hand side. Yeah, so if we have the rule S arrow ASB, this is the order we want from top to bottom on the stack. So we kind of turn it 90 degrees that way and then put it on the stack, 90 degrees clockwise. What do we do next? Yeah,
The S goes to an A because there's nothing we can do with the S directly to make the character B. So you have to transition it to an A.
what can the A go to? Because that's not the character we're looking for, so we need something to do to that A to get there.
We can pop the A and then A goes to B A lowercase a.
Excellent.
Now the character on top matches the character we're looking for, so we
Yeah.
can pop it.
Good so far. Anyone have any questions on the work we've done to date? This is basically another way of thinking about what we've done all quarter. A can go directly to a C. So here is how I would finish this off. Yeah.
Is that a Q slowly evolving into an A? Or?
Yeah, it's always a Q, but it is very slowly evolving into an A, you're right. In other classes I teach, you will learn about the evolutionary algorithm. I'm just applying it to the Q as it slowly becomes.
It's like the progression of man.
Yeah, exactly. Those are meant to be Qs, but as we know, I have the handwriting of a second grader.
That's insulting to the second grader.
I know. My handwriting has gotten worse since I was in second grade. Any questions on this? So I guess the question I would have for you is, where in here did we have to apply a guess? Or were there multiple options and we had to make an intelligent selection about where to do that or what to do?
When you mean guess, are you talking about like an assumption or like a planned road ahead? Because whenever
Yeah.
we do like the S, we trends when we went from S going to A, S, B because that target was in range.
Yes.
Yeah.
What other options were there? We could have replaced the S with an A.
Yeah.
So here, we made an intelligent decision about if we make the S an A, there's no way to create this look ahead, but that required an analysis of the grammar programmatically. It's something that we as humans can see very easily, but as a computer, you would have to look ahead and play around with and actually search that space. Same here. Same here when we replace the A with a BAA instead of a C, and then same here. So wherever there was a non-terminal with multiple options for how to proceed, we had some kind of procedure that we needed to go through that as humans, we just look and figure it out logically, and as a computer, we'd have to go explore the options. The purpose of the LL parsing algorithm is to make this so we don't have to search or guess. So this is the parse as we've done it this quarter. We're going to learn an algorithm to remove the branch at each of these spaces so that we know what to apply with a constant time lookup rather than having to search a larger space. Anyone need anything else from the board before I make it go bye-bye? I say that and then erase it very quickly. You gotta be on top. This is the caffeine check of the morning. All right, I think this is what I produced. All right, so how we're going to do this. We're going to use this concept of a look ahead, but we need to store it in a table. So that via some analysis of this grammar, using first and follow, as we discussed yesterday, we need to be able to look up in that table which production to apply if we want to map a particular next character in the string to one of the possible expansions of that non-terminal. And that is something that we could do as a pre-processing step before we actually go through the compilation process, the parsing process. So this table, rows of the table are all non-terminals in the grammar. And columns are all terminals in the grammar, as well as the end of string marker $. This is going to be called the LL1 table. And the process to fill out each of the cells of this table is, for every production in the grammar, for every terminal in the first of the right-hand side, add right-hand side, the entirety of that production to the cell in the LL table of row left-hand side and column, the terminal that appeared in the first of the right-hand side. Let's give you a sense of what that looks like. There is one extra rule. If lambda appears in the first of the right-hand side, add the right-hand side for every element in follow. At the end of that process, every empty entry in the table allows us to immediately fail. So if we have a lookup that is in the column and we have a row that is the non-terminal, that is the top of the stack, and there's nothing in that cell, we can immediately stop the parsing process and say this grammar cannot generate that string. If it does exist, then we can continue the process applying the right-hand side that is in the cell. So I'll give you an example. This is actually much more straightforward than it sounds from that process. So let's build the LL1 parse table for this grammar. And the way you're going to do this is you first calculate first, and then following that, you calculate follow. So let's start with calculating first and follow for this grammar. I think this is something we've already done. But let's do it again, because repeated work is fun.
then you can also look at A, S, B, S goes to A. S, B, right after that. So it's on the right hand side.
We follow A. It's not that C follows A, rather it's that A becomes C.
Right,
So would the dollar sign mean they follow?
yes.
So all S would also include. Is it all signs of the tree? Even S, which is actually one cell. So whatever is in this equation. Is the issue. Anytime, so in the case of this, where A, there's a there's trunk after A, so you like A, C. That's. Actually, it's two. It's working.
All right. We ready to compare? Here's the answer. What is different between what you have and what is here? Anyone who can identify a difference? I will happily explain why this is right. Yeah,
Why is B in the follow of A?
why is B in the follow of A? So if we have S arrow ASB, this S becomes an A. And after we derive this A, the next character that follows is a B. Any other explanations? Any other differences between what you have and what is here? All right, time to construct an LO1 parse table out of this. This is where everything comes together. All right. Parse table for each non-terminal. We know that we are going to, with this first and follow, be able to create let's actually do this without the algorithmic process first. We have non-terminals S and A, and we have terminals A, B, C, and dollar. So that will be our LL1 table. And I haven't drawn these wide enough, but bear with me. So what are all of the ways for S to become A as its first character in its derivation? Or is there a way? And the answer is that this S can become ASB, where the first character produced is A. So you can imagine in this parsing process that we just completed, that what's on top of the stack is an S, and the next character in a look ahead is an A. The question is, which of these productions should we apply to eventually be able to shift past that A? And the answer is ASB. So that's what's going to go in this cell. Is the entirety of that right-hand side to tell us that when we're in that case, this is the production that we should apply. How do we know that from first and follow? Because A is in first of S, that means it can be derived. So we can now look at every production and figure out if it's possible to derive that, how do we derive it? How about from S to B? Which right-hand side allows us to produce B directly? It doesn't have to be directly from S, but via some sequence of productions.
S to A.
Yeah.
A to B.
It doesn't matter what it is after that, it just matters that the right-hand side of A is all that gets stored in the table, which says that we should do that, and then whatever appears next, we can solve it from there, and that will also be apparent in the LL1 parse table. From S to C, how do we get there? An A. Can S go to dollar?
Not as part of the first.
Correct. Yeah. So we're gonna say that if we're at the end of the string and there's an S on top of the stack, there is no way to remove that S without reading additional characters. So we leave it blank. So how about A? Is there, if we look at first of A, is there a way to generate A from A? No, there is no way to do that, so we leave it blank. How about from A to B? It's the BAA, and again, I wish I had drawn this a little bit wider. How about A to C? It's the C. A to dollar, not in the first. And the reason we don't need to use the follow here is because there are no lambdas in the first of any of these, and there's no lambda in the grammar. But if there were lambda in the grammar, then we would need to utilize the follow portion of this table to continue to fill out this. But this tells us now how to remove the ambiguity from the parse on the prior slide. We just do a lookup into this table that says, when we see this non-terminal, and we want to, and we see this character as the next character on the, in the string, then that row column tells us which production to apply.
If
Yeah.
there is some natural ambiguity in the grammar, would you have to have both the different possible derivations?
Yes, and we'll actually get into that.
Gotcha.
That means that the grammar itself is not LL1. It might be LL2, where you need to do a 2-character lookup into the string. It might be LL6, where we need to do a 6-character lookup into the string. It might not be LLK for any K, in which case we have to resort to using CYK instead of a more efficient parsing process like this. So that's the short answer to that question, but we will get there. Other questions on how to create this table? It is simpler than it sounds when you describe it algorithmically, but I want to give you an intuitive look at it first.
Yeah, but just wait till it hits the following question.
Yeah, and if it is the last project.
Just wait till we have to do it, give them 15 to come along.
So this is the algorithmic process. We built the table. For each right-hand side of a production that starts with a terminal, add it. For the right-hand side A, so this is derived from S. add it to LLSX, where X is each element of first of A. And that gets us the exact same table that I just described. Questions on the algorithmic approach to it? Again, these slides will be available for reference as you build this out yourself. Yeah, question?
I guess my question is like in the actual implementation of this. Is this something that should be happening dynamically or just generated initially?
It is a pre-processing step to the grammar. So yeah, you read in the grammar, you'll build the parse table, and then you'll go through the parse process. And whenever you have that ambiguity of there's a non-terminal on the stack and there are multiple possible right-hand sides that can be derived from that non-terminal, then you'll do a lookup into the parse table that you created and apply the associated rule that is there at the table, rather than having search. All right. Subroutines for LL1. Push is going to push the string W onto the stack from the rightmost character to the leftmost. Top returns a copy of the top symbol of the stack without popping it. It's the exact same thing as a peek. And we have pop, which does exactly as you would expect on a stack. Get is the next look ahead symbol in the input string. And that's basically all you should need. It's just a fancy stack. How do we terminate? The strings in the language which says that we're in Q2 and the stack has a Z on it, then we accept. If at any point you have a non-terminal on top of the stack and you go to do the lookup in the LL table based on the symbol that you need to shift past next and it is empty, you can immediately stop with an error. There is no way to produce this string and there's no reason to continue trying to search for it because it will not be there. There is no way forward. So here's some pseudocode for the overarching LL1 algorithm using those terminology, that terminology from the last slide. So push S, that is the transition from Q0 to Q1. You grab the look ahead from the string. While the stack is not empty, we're going to peek at the top of the stack. If it's a terminal, then if the symbol is the look ahead, then do a shift, which is the equivalent of a pop and get the new look ahead from the string. Otherwise, if there's no possible way to produce that symbol, if that's not the case, then you have an error. There's no way to replace that terminal with something else. So the terminal, by the time it's on the top of the stack, it needs to be the character that is used in that is the next character in your strings look ahead. If the symbol is a non-terminal, then we do a lookup to the LL table at the symbol look ahead cell. If there's an element there, then we pop the non-terminal off the stack and push the right-hand side that is in the LL table, again from right to left, exactly as we defined push on the last slide. So that's going to be a multi-character push onto the stack of each of those symbols. Otherwise, if there's nothing in the LL table for that, then we have an error. By the time this loop terminates, if the look ahead is something other than the end of string marker, that means we emptied the stack and there are still characters to parse, which is an error. Otherwise, we know we're at the end of the string and we have an empty stack, therefore we can accept, which is what would have been necessary in the NPDA in order to transition to Q2 in the first place. So overall, it doesn't look too bad. Of course, devil is in the details, as usual. As well as you'll need to, as subroutines for this, to be able to build that LL table, you need to be able to calculate first and follow. Then you'll need to be able to build the LL table. Then you need to be able to parse the grammar to fill the LL table. Once you've done all of that work, then you can implement this algorithm. All right, same grammar as before. If we apply the LL1 algorithm to this, we show the contents of the stack at each step, just like we did before. Show the contents of the look ahead, just like we did before. And we get exactly the same thing, except that now we don't have to keep track of the state because we're not modeling this off of an NPDA. We're just utilizing the LL1 parse table that we created from before to resolve any ambiguity. So it just looks like it did before, except again, no state. So take a second, look at this, look back at your LL1 table and make sure that when there is an S on the stack and a look ahead of an A, that table tells you which right-hand side of the S to apply there. There's no guessing involved, and it doesn't require anything on your part, the human, to know which one to apply. It's there in the LL1 table. At any point that there is a non-terminal on top of the stack. So we will look up to the LL1 parse table. This is the row, this is the column, and that tells us to replace this, that. When this is the row and this is the column, it tells us to replace this with that. When this is the row and this is the column, it tells us to replace this with that. When this is the row and this is the column, it tells us to replace that with that. So those are the steps in here that have a lookup to the LL table. And there is now no interpretation needed. They're just lookups. Questions on that? Cool. As we saw earlier, and as Nathan pointed out a couple minutes ago, not all grammars are LL1 in nature. There are some grammars where there ends up being options or ambiguity in the LL1 parse table. Let's get a sense of what that looks like. So what it means is that we can't resolve the ambiguity in the grammar with a single character look ahead. We may need to look ahead more characters into the string to be able to resolve that. And it may not matter how many characters we look ahead into the string. There's no way to resolve it with any look ahead size. So some are not LLK for any K at all. How would we figure this out? And the answer is just to look for a conflict in the LL1 table. If at any row, column, cell, there are multiple right-hand sides, then we have a conflict or we have ambiguity. So at least one entry in the table has more than one right-hand side in that cell. So let's take a look. Go ahead and build an LL1 parse table for this grammar. Start as always with first and follow, since there's only one non-terminal in this grammar. What's first of S?
A,
What's follow of S?
B dollar sign?
Yep. Now build the LL1 parse table. How many rows are in the LL1 parse table? Just one. How many columns? Should be 3 columns. 1 row, 3 columns. S is the only row, A, B, and dollar are the columns. And this is the simplest example that we can find of a grammar that's not LL1, because we immediately see a conflict. Where's the conflict?
It's in, A,
Yeah,
in the column for,
row S, column A. Table looks like this. There's no way to produce a string that starts with a B. There's no way for the S to be empty and go to nothing. But there are 2 different ways for that S to create a string that starts with an A. So if we have a look ahead of 1 and we see an A, which production should we apply? The left-hand side or the right-hand side? Or the left or the right? And the answer is we don't know. We need more information to be able to do this. So yeah, we can't decide between the productions of the right-hand sides, the left or the right-hand side, with a single character look ahead. But we could build an LL2 parse table. Any guesses of what an LL2 parse table would look like? What's the difference? What's going to allow us to remove this conflict?
Will it have possible combinations for every one of the first 2 letters? So it have
Yes.
A, B, B, A.
That is exactly right. But it's also going to include dollar as well.
Okay.
So yes, we need a column in the table for every possible pair of symbols. And as we do this, we find that we have AB, a dollar, BA, BB, B dollar. And of course, the first character could also be dollar, in which case nothing can follow the end of string marker. So we need a column for that as well. But we see that if we want to produce the string AA from this, then there's only one way to do that, and that is by going through a SB. And there's only one way to produce AB, which is to go from the right-hand side to produce AB. There's no way to produce any of those other sequences of characters. So depending on a 2-character look ahead, we can remove that conflict. And then when we were to actually go do the parse, instead of having a look ahead of size 1, we would have a look ahead of size 2. Be looking for the next 2 characters in the string. And we would need some way of mapping the next 2 characters in the string to what's on the stack. Any questions on this? All right, let's grab the next example. It's gonna be a little bit of work. But determine the value of K for this grammar. How far ahead of a look ahead do we need to be able to have no conflict in the LL table? And the way you're going to do this is by looking at the number of look aheads. And we need to take the maximum of all of the non-terminals. So if to resolve C, we only need to look ahead of 1, and to resolve B, we need to look ahead of 3, and to resolve S, we need to look ahead of 2. Then we take the maximum of that. Say we need to look ahead of 3 characters in the worst case in this grammar. But that is not necessarily the case. So what is the value of K? I'll give you the rest of class to think about that, and we'll come back tomorrow and we will get an answer.
I wonder if you can make, I wonder if you can make some kind of machine learning algorithm to recognize the pattern of languages by doing parsing on a bunch of different strings, trying to get it to recognize the pattern of the language.
I think we can do better than machine learning. I think we can have a direct algorithm to do it.
But I thought there was no direct algorithm for that.
For exactly which problem to recognize.
The pattern of a language from based on grammar.
Okay, so you're thinking of identifying a loop or identifying a program that terminates or not?
No, I'm talking, yeah, I mean, like, talking about like taking a grammar. And then, but I thought there was no algorithm to turn grammar into like a properly defined language. Like,
Depends on the grammar,
depending on the grammar.
not in general for any grammar.
Yeah.
But if the grammar has particular forms to it, like an LL grammar can be mapped efficiently.
To a language, specific language.
Yeah.
Well, I mean, I know that it can do what accepts it and what, you know, obviously this is what we're doing,
Yeah,
but that's the same thing as actually finding a language from it.
that's exactly the same thing. That's why we're able to write any mathematical logic in any programming language that we have, and we have an ability to translate that into something that can be run efficiently. It's because it's a logical language. Defines the entire meaning of anything we could state logically. There is a way to state that in that language.
You need to have. K has to be the length of the string for whatever you're checking. Because. Depending on if you take the derivation where you go A capital B or A capital C, you can end up with D. Never mind, I saw something I missed.
Yeah. It's not the entire length of the string. It turns out that there either is a value as a constant value of K that will work regardless of the size of the string, or that there is no such K, regardless of the size of the string. One of those is right. But we will come back to that tomorrow. If it bothers you and starts to affect your sleep, might as well solve it.
It's 4, but I keep like.
Listen. For the fun problems. Yeah, that's it for class today. I'll see you tomorrow. I'll have office hours in an hour. For anyone with questions.